Hello, we are at lecture 16 for differential equations and linear algebra, and we are now at the point in the course where the connections between differential equations and linear algebra are getting very strong. Lectures 16a is about differential equations, 16b is about linear algebra, but within both lectures I'm going to refer back and forth between these two topics, differential equations and linear algebra, emphasizing the ties between them. Here in lecture 16a, we're going to continue talking about damped harmonic oscillators. I'm going to look at an example. I'm going to find the solution to a damped harmonic oscillator, IVP, by guessing and using linear algebra in two key ways. One is a real basic application, just using row operations to solve a system of linear equations. A second application of the linear algebra is kind of a higher level theorem based on vector space approach that we need to finish the problem. We'll also look at what are called completely and partially decoupled linear systems involving matrices that have a special form. And I will also introduce in this lecture the idea of a matrix exponential, which we'll get more and more in depth on in later lectures. 16b, you can see, is mostly about vector spaces and linear transformations, but I have this key topic that I wanted to do quickly: elementary matrices, row operations, and calculating the determinant of a 4x4 matrix with those things. It's a pretty cool thing. All right, so let's look at our example of a damped harmonic oscillator. We have a particular damped harmonic oscillator equation that's modeling the motion, say, of a mass in a spring, though of course there are other harmonic oscillators, as I've mentioned before, like electrical. The second derivative of the position with respect to time, which is the acceleration, plus 7 times dy dt, which is the velocity, plus 10 times the position itself, equals 0. This is a second order equation because it involves a second derivative. It's also scalar because it's a scalar quantity that we're after. Y is a function of t. This is a linear operator, as I mentioned before. That's why it's a linear equation, and it's homogeneous because the right-hand side function is 0 when I get all these things on the left. We do have two initial conditions: y of 0 equals 3, and y prime of 0 equals -1. So I pull that mass from rest 3 meters to the right. Okay, this is a very big spring. And then I don't let it go from rest. I give it an initial velocity of -1 meters per second. Maybe it's like I hit it with a hammer or something really hard to have an initial velocity at time 0 of -1 meters per second. How do we solve this? We can solve not just by any old guessing, but by educated guessing. Now, we've talked about how solutions of these kinds of equations often involve trig functions like cosine and sine. And in lecture 15a, we also saw it involved an exponential decay when we had damping or friction present. The friction here, so to speak, the 7 coefficient, is fairly large. It's a fairly large amount of friction. You might say maybe there's no oscillation at all. And based on that guess, you might guess that y equals e to the st is a solution for some value of the constant s. Think of s as a constant. I don't know for sure if that's going to work. Actually, I do, because I know it's going to come. But let's just pretend we are hoping it will work. The question then would be, what value of s will make it work? What would s have to be if this is going to be a solution? So how do you do it? You just substitute this function that you are hoping is a solution into the left-hand side of the differential equation, simplify, set it equal to 0, and see if there's some value of s that makes it equal to 0 for all values of t. So find its derivative and its second derivative. Y prime with the chain rule is s e to the st. Remember, s is a constant. We are differentiating with respect to t here. Second derivative, we'll get another factor of s. We'll get s squared e to the st. Now substitute those things into the left-hand side of the differential equation. Y double prime is the same as the second derivative of y with respect to t twice, plus 7y prime plus 10y. Plugging in this function and simplifying by factoring out a common factor of e to the st gives me this expression. And I'm setting this equal to 0 for all t, and I'm wondering, are there any values of s that will make that equal to 0 for all t? Well, e to the st can never be 0. So the only way that's going to happen is if this thing in front, this quadratic in s squared plus 7s plus 10 equals 0. But we can find two values of s that make that 0. You could use the quadratic formula, or in this case, we can just factor as s plus 2 times s plus 5, so that s is -2 or -5. And evidently that means that these two functions, y equals e to the negative 2t and y equals e to the negative 5t, so s is negative 2 and 5, negative 5, are the only possible solutions of this differential equation. The only possible. Okay, the logic is we were assuming that this is going to be a solution, and based on this work, we're showing that if that assumption holds, then these would be the only possibilities. But does that mean they are truly solutions? Technically speaking, logically speaking, you have to check them in the ordinary differential equation to truly prove that they are solutions. But that's easy. Just do left-hand side equals right-hand side. We'll take, for example, the e to the negative 2t. Find its derivative. You're doing the same calculations you did before in the general case for s, but now s is negative 2. Use the chain rule again. Plug that back into the left-hand side of the differential equation. It's very similar kinds of calculation. It's just a different assumption. We were assuming e to the st was a solution before, and we were deriving what s would have to be. Here we know what s is, negative 2 in this case, and we're seeing it does solve the differential equation. But again, the calculations are not really any different, just less general. So we're just checking when we plug all these things in here. I ultimately get 4e to the negative 2 minus 14e to the negative 2t is negative 10e to the negative 2t plus positive 10e to the negative 2t is identically 0. Maybe put 3 lines there to emphasize that it's identically 0 for all values of t. Remember, my upside down a means for all. And that checks it, and that logically proves that e to the negative 2t is a solution. Similar calculations would verify that e to the negative 5t is also a solution. I'll leave that to you to check. How about the general solution? We need some, it's at this point we need some high-level linear algebra involving vector space ideas, which I introduced in lecture 15b and will continue in 16b, that apply to this kind of situation. What we're really after is something called the solution space when we're after a general solution. What's a solution space? It's the vector space of all possible solutions. What does that mean? That means it's essentially the set of functions that are all possible solutions. And those functions do form a vector space. They satisfy all the axioms in the definition of a vector space that I talked about in lecture 15b. And I will again re-emphasize in 16b. You add to any two solutions, you're going to get another solution. That's closure. We're thinking of the functions as being vectors, not in the usual sense of vector, but in a more abstract sense, these algebraic properties. Closure happens. Add two solutions, you get another solution. Commutative property. You can switch around the order of the functions in this vector space. Associative property. There's a zero function. There's a zero vector. It's the zero function. The zero function does solve this differential equation. Its second derivative, its derivative, itself, they're all zero for all t. There is a zero vector, it's the zero function, etc. Some theory that we'll get to in lectures to come is that when you have a linear second order or ordinary differential equation like this, its solution space must be two-dimensional. What does that mean? Does that mean it's a plane? Well, only by analogy. What it really means is that it's got what's called a basis of two elements, in this case two functions. And in fact, these two functions, e to the negative 2t and e to the negative 5t, form the basis. They are linearly independent, they're not multiples of each other, and they span the solution space. Any solution is a linear combination of them, and that's what we're about to use. Any two linearly independent solutions will span the solution space, so the general solution can be written like this. Again, e to the negative 2t and e to the negative 5t are both solutions. And they are linearly independent. They're not constant multiples of each other. The solution space is two-dimensional. That means they will form what's called a basis for the solution space. And that means any solution can be written as a linear combination of them. This is going to make more sense if you watch lecture 16b. I'll refer back to it. To solve the IVP, so that's the high-level application of linear algebra. Now we're about to do the lower-level application of linear algebra. We're going to solve for K1 and K2. To solve the IVP, start by finding the derivative. Differentiate this, use the chain rule. You get negative 2k1 e to the negative 2t minus 5k2 e to the negative 5t. Now use the initial conditions. Y of 0 was 3, and therefore 3 equals y of 0. Plug in t equals 0 into that. Get e to the 0 here and here, so those are 1s. It simplifies to k1 plus k2. There's one linear equation in the two unknowns k1 and k2. For the second linear equation, use the initial value of the velocity rho. -1 is y prime of 0. Plug in t equals 0 here and here, get negative 2k1 minus 5k2. There's a second linear equation in k1 and k2. I want to solve this system of linear equations for k1 and k2. You don't have to do it this way, but we might as well. Let's go ahead and put them in an augmented matrix. So the first row here represents 1 times k1 plus 1 times k2 equals 3. The second row represents negative 2 times k1 minus 5 times k2 equals negative 1. Do row operations to reduce row echelon form. We've got a leading one there already. Multiply row 1 by 2 and add it to row 2 so that this becomes a 0. But you do need to do the other calculations. 1 times 2 is 2 plus negative 5 is negative 3. This will become a negative 3. And 3 times 2 is 6 plus negative 1 is going to become a 5 in the lower right corner. And yes, we see the negative 3 and the 5. This is still an augmented matrix. The next step is to get a leading one in the second row. Divide row 2 by negative 3, or in other words, multiply it by negative 1/3 to get a 1 there and get a negative 5/3 there, like you see there. Just one more step. This is echelon form, but we want to get to reduced row echelon form, so we want to get a 0 above any leading one, like this leading one. We can't above that because there's no rows above it. So multiply row 2 by negative 1, add it to row 1, putting the answer in row 1. This becomes a 0. This stays a 1 because that's a 0. The only calculation you have to do is to figure out what the new number there is. So we'll have negative 1 times row 2 gives you positive 5/3 here. Positive 5/3 plus 3 is positive 5/3 plus 9/3 is positive 14/3. Now we are in reduced row echelon form, and the corresponding linear system tells you that k1 equals 14/3, k2 equals negative 5/3. Logically speaking, we have only derived possible solutions to know and logically know they are solutions. To prove it, you'd have to plug them back into the original equations. You can do that and verify that they do solve them. I guess we can do it real quick in our minds here. K1 plus K2, this plus this equals 9/3, which is 3. Solves that one. How about negative 2K1 minus 5K2? Negative 2 times this is negative 28/3. Minus 5 times this is going to be negative 28/3. What will it be? Plus 25/3 is negative 3/3 or negative 1. It works. And this means our unique solution to the initial value problem is this single function, this single scalar function here. Plug in k1 is 14/3 and k2 is negative 5/3 into that formula there, and you get this formula here. This is a general solution. It represents infinitely many solutions. It helps you solve any initial value problem. This is the unique solution of the initial value problem that we're given. All right, as always in this course, as we've been doing recently, we want to also think about this as a system. Think about the corresponding linear system and vector solutions. Why? Because it's going to be helpful to think about phase planes. In the linear case, understanding linear systems and their phase planes will help us with harder situations where we have nonlinear systems and nonlinear phase planes. So, introduce a new variable. Let v be dy dt. In other words, v is the velocity. The corresponding initial value problem in matrix/vector form is then this. Think about it. So capital Y really represents the vector whose components are little y, little v, as we've been talking about recently. These things are functions of t. And since dy dt there equals v, and dv dt here equals negative 10y minus 7v, we can say these two vectors are the same. Where did that dv dt equation come from? It came from the original second order scalar equation. Let me write it on the board. The original second order scalar equation with prime notation was y double prime plus 7y prime plus 10y equals 0. So in other words, v prime, dv dt, is y double prime, is subtract 7y prime and subtract 10y from both sides, negative 10y minus 7y prime. In other words, negative 10y minus 7v. And that's what's going on here. We've got a negative 10y minus 7v. That can be written as a linear combination of these two column vectors, 0, 10, 1, negative 7, with y and v as the weights. I skipped that step here. This can be thought of, therefore, as a matrix times a vector, as we've been talking about. This matrix would be my matrix A for this corresponding linear system. And we have an initial condition as well as an initial vector. Y of 0 equals y sub 0, boldface vector. A vector whose components are unboldface y sub 0 and v sub 0, which are 3 and negative 1. We're now going toward the phase plane, a solution in the phase plane. The unique solution of this, as a parametric curve, can be found using the solution to the scalar equation from the previous slide. Plug the answer in for the first component and differentiate it for the second component. And get this, right? This thing right here, that was the answer for little y from the previous slide, right? 14 thirds e to the negative 2t minus 5 thirds e to the negative 5t. That is little y. Differentiate it to find the velocity and put it in the second component. The derivative of this is going to give you a negative extra factor of negative 2. Negative 2 times 14 thirds is negative 28 thirds. With differentiating this, you get an extra factor of negative 5, giving you a plus 25 thirds e to the negative 5t. That is the solution as a parametric curve, as a vector-valued function of t, time. We'd like to graph it in the phase plane, which will have a y-axis horizontal and a v-axis vertical. Before we do that, we can also graph little y and little v individually as functions of t with ordinary graphs. That's what you see right here. And when you look at these ordinary graphs, y in blue, v in red, you should take a few seconds to think about, say, the motion of the mass in a spring. What is this telling you about? Remember, the situation was we were pulling it 3 meters to the right. We're getting some big spring. And, well, essentially giving it an initial velocity that's negative. We're not letting it go from rest. We are like hitting it with a hammer to give it an initial velocity of negative 1 meters per second. What happens? There's enough damping going on here that there's no oscillation. There's no cosines and sines in the solution. You see the blue curve decay towards 0. The leftward velocity in absolute value actually gets larger at first. You can see that red graph is further from 0. This graph here gets steeper with a negative slope. That means the mass does speed up initially. Makes some sense. The spring is pulling on it, trying to accelerate it. But we do reach a point at about t equals negative, I don't know, 0.3 seconds or something like that, where the leftward velocity as an absolute value in speed is maximized. It's moving as fast as possible to the left, and then it starts slowing down. And it never reaches equilibrium here, at least according to the model. But remember, in real life, it would get so close to equilibrium that it would seem like it has. It would seem like it stopped. And maybe you would even say it has stopped. And in a sense, that's a defect of the model. The model says it would never quite stop. It only asymptotically approaches stopping. For all practical purposes, it does stop, with no oscillation. Okay? You should be able to go back and forth between this graph and the graph of the solution curve in the phase plane. So what do we see here? We see the phase plane. We see the horizontal axis labeled with a y. That's the position. We see the vertical axis labeled with a v. That's the velocity of the mass on the spring. We see a vector field in the picture. Really, it's more of a direction field because I use Mathematica to make all these arrows have the same length. You should remember from previous lecture A's that for the true vector field, defined by this formula here, by plotting outputs of that when you plug in different values of y and v, the vectors are not all the same length. And with these kinds of systems, what happens is, well, there's an equilibrium point at the origin. There tend to be very small vectors near the origin, and as you get further away, they get bigger, they get longer. Indicating, since the solution curve not only follows these arrows in a tangential way, but it also affects the speed of the motion along the curve. The speed is quickly at first, a large speed, I should say, and then it slows down as it approaches the origin. That's what you would see if we animated it. I didn't bother animating this one, but that's what you would see. We also see some null-clines in here. This light blue line that's the same as the y-axis is evidently the y null-cline. dy dt is 0. Why? Because the vector field vectors are pointing straight down over here and straight up over here. dy dt is 0 when v equals 0. Hey, that makes sense. dy dt equals v. So it will be 0 when v is 0 along the y-axis. That's the first or horizontal null-cline. It's labeled with y here. In general, it might be labeled with x. The second null-cline, the v null-cline in this case, is where dv dt equals 0, negative 10y minus 7v equals 0. Where does negative 10y minus 7v equals 0? Solve for v as a function of y, and you'll get v is negative 10/7 y. That green line has a slope of negative 10/7, and it goes through the origin. The vector field is horizontal along there. This vector, you can see right there, is pretty close to horizontal. This one down here that you can't really see is pretty close to horizontal. Solutions cross the green line with a horizontal tangent, like right here. There's a horizontal tangent. The velocity vector for that solution curve at that point would be pointing directly to the left. Its v component would be 0. The second component would be 0. You should be able to go back and forth and see the relationships between these two graphs. Y always stays positive but decreases towards 0. Just like along this pink curve, y is always positive but decreases towards 0. V is always negative. Starts at negative 1, goes down at first before going back up towards 0. Just like this curve, starts out negative at negative 1 in fact, goes down at first before coming back up towards 0. Staying negative. V is negative. This is telling you about the motion of the mass as well. That again, it is, again, pull it, hit it with a hammer, it starts moving, goes faster at first, and then it slows down, but it never oscillates. It asymptotically approaches equilibrium. That pink curve is one solution, the solution of the initial value problem. Notice again, the initial condition here is at y equals 3, v equals negative 1. There's also infinitely many other solutions depending on infinitely many different initial conditions. If you use StreamPlot in Mathematica, you can get this kind of picture. And in a sense, this is supposed to be showing lots of solutions. The red arrows are vectors in the vector field. Those are all straight. Those blue arrows are not true vectors in the usual sense because some of them are curved. You can see it, for example, this one here looks very curved. They're supposed to be connected to each other in a sense, representing solutions moving around the phase plane. And in analogy with phase lines, it seems like the origin here is some sort of sink. A two-dimensional sink instead of a one-dimensional sink. Does that mean the derivative of the vector field is somehow negative here? Kind of, but we won't explain exactly what that means until a month or two from now, or I don't know how many lectures it would be, maybe 10 to 15 lectures from now, we'll get into what that means. All right, we also want to look in this lecture at completely decoupled systems and partially decoupled systems, and I do want to show you some Mathematica at the end. Hang on, I'm going to show you some pretty cool things of Mathematica, I think. What's a completely decoupled two-dimensional linear system? What are the corresponding solutions, and what does the phase plane look like? In general, a two-dimensional homogeneous first-order linear system is one that can be written in this general form. d vector y dt, boldface capital Y, equals, okay, now we're going back to x and y instead of y and v, dx dt dy dt for the components, equals linear expressions involving x and y, with no constants being added. This is like a linear transformation, which can be represented as a matrix times this vector boldface y. You can call it A times boldface y, which is very analogous to the scalar case, dy dt equals ay, whose solutions back in the first few lectures we guessed, or separate variables too, as being arbitrary constants times e to the at, where in fact that arbitrary constant, if you have an initial value y, is the same thing as the initial value of y. We're about to see some analogs of what's going on there in this matrix exponential idea that I referred to at the beginning. Such a system is said to be completely decoupled if A is a diagonal matrix. Now, in some lecture B's recently, I talked about diagonal matrices in relationship to determinants. So there's special kinds of matrices. They have zeros both below and above the main diagonal that goes from upper left to lower right. Here's an example of a completely decoupled system. Notice the zeros here and here. The A and D are not necessarily zero, though they could be zero, one or the other or both. But for sure, off of that main diagonal, that's the main diagonal from upper left to lower right, we have zeros. Why is this special? Because it is a completely decoupled system. There's no relationship between the dx dt equation and the dy dt equation. There's no interaction between the variables there. That's why it's completely decoupled. You can think about each scalar differential equation separately and then just merge them together to get a vector solution. And these equations are like the ones I erased. The solutions of that, well, this one's going to involve x is going to be an arbitrary constant times e to the at, and y is going to be an arbitrary constant times e to the dt. Where a and d are numbers. Here's what I'm about to show you there. Yeah. Arbitrary constant times e to the at plus, and that's for the x, first component, arbitrary constant times e to the dt. Which, if you like, you can split apart as a linear combination. And yes, if you're thinking this, yeah, that means these two vector valued functions, parametric curves, span the solution space. Okay? They form a linearly independent basis of the solution space. And I can write the general solution as a linear combination. In the previous example, we were talking about scalar valued functions, e to the negative 2t and e to the negative 5t, that were linearly independent, not multiples of each other. Here in the vector case, we've got two vector valued functions, parametric curves that are not scalar multiples of each other. They are linearly independent. They won't be a basis for the solution space. And the unique solution of a generic IVP, and because of some typesetting, I took the liberty of introducing a new idea here. With y of 0 equals x0, y0, what's this t here? That t is called transpose. I'm taking the liberty of introducing the idea of a transpose, which we will use later, because I didn't have enough room to write a column vector here. When you write x0, y0 transpose, what you really mean is that is shorthand for the column vector x0, y0. Transpose essentially means take a vector and flip it in a sense, and at least with a row vector, flip it to become a column vector and vice versa. And actually, I wouldn't have to put the comma in there. And in fact, you usually wouldn't with a row vector, but it's not a real big deal. We'll come back to using transposes more later in the class. A generic solution of the IVP can be written like this. Focus on that first. Notice the constant k1 equals x0, the initial value of x, k2 equals y0, the initial value of y. Here I'm thinking of k1 and k2 as being arbitrary. Here I'm thinking of x0 and y0 as being fixed. We can write that as a linear combination like this. We can write it as a matrix times a vector like that. We can give this function a name if we want. What's this? Capital phi sub boldface y0 of t. Remember I've used lowercase phi for solution names before? Now I'm using a capital phi, or phi if you prefer, for a vector valued solution with this initial value, this initial point when t is 0. And you can check that it works when you plug in t equals 0. You definitely get that. And look at this. Question mark, question mark, question mark. Should I write this matrix times this vector as e to the capital A times t times the vector? Is that a good idea? What would I be saying in this? Writing this, I'd be saying, well, capital A is a matrix. It's this matrix right here. And in the completely decoupled case, capital A is right there. Would it make sense to call this matrix e to that matrix times t power? I mean, after all, the a becomes e to the at, and the d becomes e to the dt. Maybe that makes sense. And I'm saying it does make sense. And it comes out nice and simple in this special case of a completely decoupled system which has a diagonal matrix as its matrix. This is called the matrix exponential. T is a real number. It's time. I'm doing a times t, the matrix A times the scalar t, which I will often write it this way, putting the t first, just to, it's sort of more common to put the scalar in front of the matrix. This is entry-wise scalar multiplication of a scalar times a matrix. I did refer to that a little bit back in lecture 15b when I talked about vector spaces of matrices. And you multiply them by scalars by doing it entry by entry, which is analogous to multiplying vectors by scalars when you do it component by component. And somehow I'm taking that matrix and I'm making it the power of e. I'm raising e to a matrix power to get a new matrix. Weird. But it is a good idea, it turns out. Weird, but it is a good idea. And partially the reason it's a good idea is because it goes back to the analogy of the other solution that I wrote back 5 to 10 minutes ago, whatever it was, this one there. For this differential equation, dy dt equals a times y. It's like the little a becomes a matrix capital A, both here and here. And the scalar y0 for the initial value y becomes the vector boldface y0 for the initial point value of y. Lots of analogies here that can be generalized. And this can be extended to bigger matrices, 3 by 3 and 4 by 4 and 5 by 5, diagonal matrices. This kind of thing gets extended. I just didn't bother writing it down. What about the node lines in the phase plate? What's the x node line for this special case, this completely decoupled system with a diagonal matrix? The x node line is going to be where dx dt is 0. In other words, x is 0. X is 0 along the y-axis. Y is vertical now. And the y node line is going to be where dy dt is 0. In other words, where y is 0, which is the x-axis. The x node line is the y-axis, and the y node line is the x-axis. And what would that mean about some special solutions? There would be certain solutions, those that start on the axes, that stay on the axes. They are called straight line solutions. Let me show you, again, Mathematica that'll illustrate this in nice ways. If, for example, A is positive and D is negative, which it could be, well, okay, first of all, the x node line is the y-axis. Say A is positive and D is negative. That means solutions that start on the y-axis here stay on the y-axis. The vector field is going to be vertical along there. And if D is negative, dy dt is a negative number times y. That's exponential decay. The arrows are going to point straight toward the equilibrium point at 0. It's going to be like a sink in that direction. And if A is positive, the y node line is the x-axis. Arrows have to be pointing horizontal along the x-axis. And if A is positive, you get exponential growth. Dx dt is a positive number times x. That's exponential growth right there. Solutions move away from the origin along the x-axis. But they are straight lines. As parametric curves, the curve is straight. What happens for other initial conditions? You might guess this, and you'd be right if you guessed this. They do curve. They got to follow those straight line solutions asymptotically. I'll let you think about that some more. Maybe draw some graphs on your calculator for a particular value of A and D. Pick A to be 1 and D to be negative 1. You'll see you get that kind of picture when you're in parametric mode. That's completely decoupled with diagonal matrices. This is our last slide for lecture A. What about partially decoupled? What does that mean? The linear system, the general linear system, where little a, little b, little c, little d are not necessarily zeros, is called partially decoupled if capital A, that matrix, is either upper triangular or lower triangular. It either looks like this or like that. This one is upper triangular. When in this triangle up here, in the upper part, the upper right part, you have your possibly non-zero numbers. Your only thing that's guaranteed to be zero is underneath. That is called upper triangular. This one's lower triangular. Your only possible non-zero numbers are in the lower left triangle that you see there. You have 0 above and to the right of it. These are special matrices as well, and they're special differential equations. They're called partially decoupled. Why? Well, because one of the equations doesn't involve the other variable. With an upper triangular matrix, dy dt's equation doesn't involve x. And with a lower triangular matrix, dx dt's equation doesn't involve y. And that means to try to solve these equations, you could take, like with this example, with the upper triangular, you could solve this one first. Just by inspection, you could say y is y0 e to the dt. Or if you're after a general solution, you could say it's maybe k2 times e to the dt. And then, based on that, you could substitute back up here in place of y and solve for x, based either on integrating factors or the method of undetermined coefficients. You might want to try that. I ended up using Mathematica to get the solutions here, partially for the sake of time for you. I will do some examples, maybe in the next lecture, 17a, of examples like this where I plug in particular numbers for a, b, c, and d. And I show you actually how to do the substitution and either using integrating factors or undetermined coefficients. But in the first case, in the upper triangular case, which is the only one I bothered with here, I could have done the same thing in the lower triangular case, the general solution can be found, but it's not so easy. And it can be seen to be this. This is what I got with Mathematica. Hopefully I typed it right. And there's no typos there. You can see it's definitely more complicated in the first component, not the second component. This is a general solution. This technically only works when a is not equal to d, because if a were equal to d, you'd be dividing by 0. So you have to handle the case where a equals d separately. And it's actually an easier case, though there is a little bit to be careful of in that case. And then if we want to solve our generic initial value problem with boldface y of 0, vector y of 0 equals the transpose of this point, which is a column vector, then you end up getting this. And again, I just typed this from my Mathematica output, and I hope there's no problems with it. Notice the similarities with the previous slide. I've got my capital phi sub y0 of t. That's just my notation for this function, this parametric curve, whose initial value at t equals 0 is this boldface vector y0. I can write it like this. I can write it as a linear combination. I can write it as a matrix times the initial condition. And then once again, we wonder, is this the matrix exponential times the initial value? Is it that? And it turns out it is. But notice that's not so easy to predict. You know, maybe you would predict a 0 there, you'd predict an e to the at there, and an e to the dt there, but you'd never predict that the upper right entry of this matrix exponential with this upper triangular matrix would look like that, right? You know, that feels like it's just pulled out of thin air. I relied on technology here. We will, as time goes on, get into details of why it works out like this, okay? Once again, we can ask about the null lines in the phase plane. The y null line is still the x-axis, so you still have horizontal motion, straight line solution along the x-axis, but the x null line is no longer the y-axis. It varies depending on the values of a and b. The x null line being where ax plus by equals 0. It's going to be a straight line in general, as you can solve for y as a function of x, and figure out the slope of that line to the origin. We'll use Mathematica here in a minute. And as I just mentioned, the x-axis consists of straight line solutions. So let's now end by looking at Mathematica quick. In this case, so this is syntax for using DSolveValue to solve the initial value problem. We are after a scalar solution here, and expand makes it look nice. So there we go. There's our solution back from 4 slides ago or whatever. I wrote it as 14/3 e to the negative 2t minus 5/3 e to the negative 5t. I can define that as a function of t like this, and I can define the velocity to be y prime, and with this code here I can plot both functions. There's where we see the graphs as functions of t. I'm using the basic plot command with some extra stuff that makes it look nice. Then I can also solve it as a system if I like. This is the system, y prime equals v, v prime equals negative 10y minus 7v with the vector initial conditions. I'm solving for both y and v as functions of t. And okay, I need to do some clearing there. Clear y and v. There we go. It stored the values that I entered before for y and v, so I needed to clear them. Yeah, this is the solution as a vector value function. By hand, we'd write this as a column vector. And I could call that capital Y of t. And here I made the solution curve in the phase plane. We see, and it's not making the arrows the same way my computer did because my computer has a more updated version of Mathematica, but the contour plot is what makes the null lines. The vector plot is what makes the vector field. The parametric plot is what makes the solution curve, this pink curve that you see. And here we can also add in the stream plot. This part right here, the stream plot makes the blue arrows that you see with the stream. That's not as cool as it could be. This is more cool. Coming to the completely decoupled systems, there's the general solution. I can write that in matrix form if I like as a column vector. I can confirm the solution is this and write that in matrix form too. And I can confirm the matrix exponentials are correct using a built-in Mathematica command called MatrixExp, which computes matrix exponentials. And this is a more interesting little animation showing you what happens as A and D change. This is the completely decoupled case. Notice you can tell from the stream plot there, you've got straight line solutions along the x and y axes. Here, A and D are both positive, but if I switch D to negative, then we get a picture more like what I drew on the board. I'm making this with manipulate, that makes an animation. My show, etc. goes inside the manipulate. My animation parameters are A and D, which you can see are here and here in this matrix, and also here and here in the contour plot. And finally, the partially decoupled system is even more interesting. Let's just go down to this picture right here. Yeah. So with the partially decoupled system, that's where only the C in the lower left corner is 0. You do have solution, no matter what A, B, and D are, you do have solutions along the x-axis that stay horizontal, though it doesn't always draw them that way. A and D do affect whether the origin is a sink or some sort of more general node, technically called a saddle point. B actually doesn't affect that, but does affect the slope of that nullcline, that x nullcline that is colored orange here. Do notice how the solution curves cross that nullcline with a vertical tangent. Wow, that's a lot to take in, but I hope you find it to be cool. Here's the code, but I will put the code into the Google Drive folder in case you want to play with it on your own. Thanks for watching.